At the actual front of consistent progress is the European Board of Trustees for Nuclear Assessment, CERN, renowned for its critical responsibilities to atom material science. Actually, the broadly well-known atom material science research focus has revealed an unimaginably fascinating finding from its colossal hadron collider that could absolutely change how we could decipher the universe. Specialists acknowledge these strange disclosures could reveal the presence of extraterrestrial life in an equivalent reality. This essential idea has begun energy and serious discussion among experts. Could this astounding exposure reshape how we may decipher the universe? Besides, whenever avowed, what huge encounters will this exposure offer into the idea of reality itself? Join us as we dive into the lately dispersed revelations, examining how CERN specialists are finishing their quietness on this chilling new discovery that can potentially change all that we know. The European Organization for Nuclear Research, also called CERN, has been notable for its adrenaline junkie tests since its inception in the 1950s. It has been at the main focus a few times for valid reasons. However, its assessments have invigorated worry about the potential plan of dark holes, cracks in our world, and various other risks. One of CERN's most notable and controversial achievements was the development of the Colossal Hadron Collider, LHC. The LHC is the world's largest particle smasher, which began its operation on September 10, 2008, and remains the latest extension to CERN's accelerator complex, crossing in excess of 27 kilometers of superconducting magnets and a series of accelerating devices. The CERN Super Collider cost more than $4.5 billion. Many would argue that this money was painstakingly spent since the LHC has resulted in some of the most significant discoveries of the last few decades, such as the discovery of the Higgs boson and various other previously unknown particles. This colossal machine is capable of speeding different particles around the ring until they reach close to light speed, completing more than 11,000 laps. The LHC does this with a series of electromagnets that produce a magnetic field inside the accelerator that is nearly 100 times more powerful than the field that surrounds the Earth. Some have expressed concern about the impact of creating such areas of strong magnetic fields on nearby devices, as well as its effect on the Earth's own field. Once these particles reach their maximum speed, many times the speed of light, particles heading in opposing directions are forced to meet in a violent collision, releasing massive energy and an assortment of particles. When particles collide, a flood of particles escapes outward, with the majority of them surviving only for fractions of a second prior to decaying. Changing the source of particles allows researchers to reveal new particles. In this tornado, exceptionally sensitive detectors are placed around the collision sites to record all the data from each crash. This sum of data mounts up quickly and requires a vast amount of investment and work to manage. The LHC's investigations produce more than 15 petabytes of raw data from these collisions, which must be carefully analyzed to extract the information the researchers need. In 2017, the LHC achieved a critical milestone by permanently storing more than 200 petabytes of data in its tape libraries. To put this amount of data into perspective, 1 petabyte is like around 250,000 movies. But what precisely are they looking for in this data? They identified something occurring with a specific type of quark or stop. Stops are the key building blocks of matter and exist in different flavors, as defined by physicists. Some of these stop flavors are unstable, decaying into various particles in the blink of an eye. The beauty of the stop, with an average lifespan of 1 in 1.2 trillionths of a second, became the center of attention due to a specific mutation. Its decay pattern differed from what scientists anticipated based on the standard model. According to their assumptions, when a stop decays, it will be impacted by the weak force and transform into a set of lighter particles known as leptons, either an electron or a muon, with the standard model predicting a 50-50 chance for both particles. However, the LHC data revealed that these stops decayed into muons 70% of the time, rather than electrons. This anomaly could exist if a previously unknown type of particle is involved in the process. This has led some researchers to theorize that a new kind of physics may be at work. A new force-carrying particle would suggest entirely new physics that could extend the standard model and answer many complex questions. The possibility of new physics challenges the standard model theory, which provides our best understanding of how the strange universe of particles behaves. The Standard Model is a scientific framework that precisely explains every aspect of our understanding of the physical world. The stunning thing is that, despite this degree of accuracy, physicists are well aware that this model is incomplete. The Standard Model only describes three fundamental forces: electromagnetic force, strong force, and weak force. Currently, there is no representation of gravity, nor an explanation for dark matter, the universe's most predominant form of matter. During recent experiments, researchers found an anomaly in the data they were analyzing that deviated from the Standard Model's predictions. While it is entirely expected to find results outside this framework, given the volume of data produced by the LHC, this time something piqued researchers' interest, and they saw the need to investigate further. What could this new force be? To explain this startling discovery, the researchers proposed the existence of a new key particle, which they refer to as Z prime, a force-carrying particle. Although this force is the most plausible option, it is extremely weak, as no signs of it have been observed so far. The scientists believe it could interact in a novel way with electrons and muons, yet the extent of its interactions with Standard Model particles remains unclear for now. If scientists were to discover new force-carrying particles, it would be a decade-long awaited breakthrough in physics. Physicists believe that if this discovery is confirmed, it will help untangle deeply rooted mysteries of the universe and make sense of old issues, such as what dark matter is and the role of the Higgs boson in modern science. Some experts believe this hidden force could help fulfill one of physics' most important goals of the last century: unifying the fundamental forces of existence. According to Elon Musk, CERN built the largest and most powerful energy particle collider in human history, the Large Hadron Collider, LHC, between 1998 and 2008. More than 10,000 scientists, numerous organizations, and labs from over 100 countries helped in this process. It sits within a 27 kilometers long tunnel on the border between France and Switzerland, near Geneva, around 175 meters underground. The first collision recorded at the Large Hadron Collider had an energy of 3.5 teraelectronvolts per shaft. On numerous occasions, that of the past world record, the energy came to 6.5 teraelectronvolts per beam. Once the LHC was additionally further developed, Musk noted that the LHC succeeds at proton beam influence. Additionally, it can speed up lead-on radiations. Specifically, proton and lead crashes are regularly led for 1 month for scientists, testing the expectations of several particle physics speculations. The essential objective of the Large Hadron Collider is to test the properties of the Higgs boson and search for the huge array of new particles anticipated by subatomic particle theories. Hadrons are composite subatomic particles comprised of quarks, which are kept intact by a strong force, much like how particles and atoms are held together by the electromagnetic force. Protons and neutrons are two examples of hadrons that are generally recognized. Included are the pions and kaons, which were first found in large beam tests in the late 1940s and early 1950s. The LHC brings two impacting particle beams together so they can interact. The Higgs boson is believed to be a major particle associated with the Higgs field. It is the quantum excitation of this field, similar to how you notice waves in the sea. The boson is like a new species in the particle zoo. It needs the quantum qualities of key matter as well as the transporters of quantum interactions, like electromagnetic force, weak force, and nuclear interactions. The Higgs boson was discovered at the Large Hadron Collider, a weighty discovery achieved at the same time by the two significant multifunctional tests, ATLAS and CMS. It was declared on July 4, 2012, at CERN. At the time, the new scalar boson was found primarily in two unusual decay channels that gave the most direct signal: decay into a couple of photons, which required an entirely quantum virtual cycle, and direct decay into a couple of Z bosons, the carrier of the neutral-weak interaction. Although the discovery of the Higgs boson at the time established the Standard Model, research into this elusive particle didn't end there. One of the major discoveries since 2012 was the confirmation of Higgs decay. According to CERN, the study of this elusive particle would continue to progress during the LHC's third cycle, especially once the Atom Smasher's high luminosity upgrade is completed in 2029. This will allow the LHC to conduct more collisions, giving researchers greater opportunities to identify abnormal physics, such as events that don't fit within the standard model. CERN estimates that when the accelerator is upgraded each year, it will produce 15 million of these particles. This compares to the LHC's production of 3 million Higgs bosons in 2017. This may help distinguish various types of Higgs boson speculations that go beyond the standard model of particle physics, predicting up to 5 distinct kinds of Higgs bosons, some of which may be produced less frequently than the basic Higgs. Even before the upgrades, researchers have provided undeniable evidence for a magnetic Higgs boson. But what difference does this make? The Higgs field was immensely large in the early times following the universe's creation. It directs the physical nature of the vacuum that exists in our space-time. It allows matter and interactions to exist as we know them, as well as the generation of mass in all known fundamental particles. Without the Higgs field and, consequently, the Higgs boson, the universe would be without nuclear particles, stars, and life. Why do you think the Higgs boson is known as the God particle? The popular media helped solidify the Higgs boson moniker, the God particle, after its discovery. It is most often traced back to Nobel Prize-winning physicist Leon Lederman, who, out of frustration, referred to the Higgs boson as the goddamn particle because it was so hard to detect. According to Business Insider, when Lederman wrote a book about the Higgs boson in the 1990s, he wanted the title to be the goddamn particle. However, the publishers disagreed and changed it to the God particle. That was the beginning of an issue between particle physics and religion that continues to concern physicists. Regardless, it is difficult to underestimate the importance of the Higgs boson and the Higgs field, as only particles would have mass under this part of nature. This suggests there would be no stars, planets, or humans, which helps explain its bold nickname. Besides the obvious need to describe the new particle, researchers continue to study the Higgs boson for 2 reasons. First, they want to understand how the very vacuum we live in originated in the early universe. Second, they want to understand how this vacuum can remain stable. The Higgs field is unique in that it sends non-zero mean predicted expected energy to the physical vacuum. This has a profound effect on our universe. Scientists believe that understanding the structure of this energy potential is responsible for the existence of electromagnetic force with infinite range and weak force with a very short range. To do this, researchers must investigate how Higgs bosons interact with one another. Also, for that, they need to create pairs of Higgs bosons. The Higgs boson contributes to the solution to the basic question of how all other major particles acquire their mass. However, its mass is yet to be fully explained. Any inconsistencies in the theory do not account for this mass and result in incidental instability. Quantum variations could destabilize the vacuum itself. Fortunately, this occurs on timescales much greater than the known lifespan of the universe. Nevertheless, researchers are still looking for additional Higgs boson-like particles that would indicate the existence of new physics necessary to explain the Higgs boson mass. All these considerations fuel the examination of much more data and, if possible, access to greater collider energy. For this reason, 10 years later, many researchers worldwide remain focused on the work. The Higgs boson was first proposed in 1964 and discovered in 2012. Scientists have wondered why it took so long. This is because the Higgs boson is both massive and incredibly unstable. To create such a massive particle, researchers had to focus an enormous amount of energy in a small container. They required a high-energy collider. Once formed, Higgs particles decay in various ways, with only a small fraction visible from the background. Scientists assembled the largest and most complex detectors to detect such particles. Then, they analyzed millions of proton collisions to find a Higgs boson signature. At any rate, will CERN's experiments and discoveries lead us to make colossal revelations? Will they send us to our ultimate end? Researchers have 3 main hypotheses about what CERN is doing. The first and deadliest theory, which has made some point fingers at CERN, is that the organization is attempting to open a gateway to hell. Some believe that CERN's experiments with subatomic particles traveling at the speed of light will propel humanity beyond the gates of hell.